Hello. Well, we've been looking at how we want to recognize flat objects. This is really the first step in taking that image that we've captured and that binary image after we found the boundary and looking at what we can do in order to extract the descriptive features that we need to do the matching. Remember, we're going to want to match some sort of line-based description with the model that we've made, which is also based on lines. Well, we want to use, now the reason why we're going to do that is because we want to use the same vocabulary for our scene description as we've got as our model description. If the two are in the same vocabulary, then it's much easier to do the matching. It's no good if you've got pixels from your image and you've got lines from your model. Having lines for the two makes it much easier. We've assumed that we've got a binary image of the part. We've assumed that we've got some sort of a boundary on the part. So let's see how we can find these lines from that binary image. Well, the first bit is we just got to find the boundary of the object. And I'm going to make an assumption here that you know a little bit of MATLAB, and we're going to have a built-in program from MATLAB called the black and white parameter, BW_param. And it's going to take an image and it's going to find the parameter pixels. So I'm saying here, find me all the pixels that lie on the parameter of the image. If you don't know MATLAB, you should look up that. Google will work just fine for that. Anyway, the net result is we've taken our binary image that we started with, and from that we have a list of the row and column positions of the pixels that lie on the boundary, and that's this bit right around here. Just for those who know a little bit more, there's a 4 right here. That says that we're interested in talking about the connectivity between the pixels in 4 connectivity, which is horizontal and vertical. There also could be an 8 in there where you look at the diagonal relationships as well, diagonal adjacency. But we're not really all that interested in that. 4 is perfectly fine. Right, so here is our pixels. Once we've executed this command, what we've got is we've got a boundary that goes around the object, and here I've just plotted it in a standard MATLAB sort of window so you can see all of those pixels. Here we can kind of see a zoomed in version of these set of pixels, and you notice there's a little bit of sort of extra pixels here and there, and in order to make our algorithm sort of go a little bit better, we're going to want to clean up some of that. So anyway, so this is what we're going to be working with, and so therefore we're going to have a few pre-processing steps. We're going to have a remove spurs, which kind of cleans up the boundary. And then we're going to do a little bit of boundary tracking, because when this BW_param command executes, it gives us a list of all the pixels around the boundary, but it doesn't guarantee that they're in any particular order, clockwise or anti-clockwise. You could have a pixel from here and a pixel from there or whatever. So that's where this next step is the boundary tracking, is it takes all of those pixels and it puts them in some sort of order as we walk around the boundary. And then finally, the last step is actually finding the corners, where we take that list of pixels and we break them up into straight line segments. And we'll be looking at that in another lecture. We'll sort of finish up at the end of the boundary tracking here. And you can see here where the initial list of pixels get modified and so on. And if you look at the web page for the course, you can actually see the MATLAB code that is used for doing all of these operations. Well, how are we going to remove the dangling spurs? Okay, so here's an example of one of those dangling spurs. This is our boundary pixels running right along here, the white pixels. And here is a kind of surplus to requirements pixel, a little dangling bit. And because of shadows and things like that, maybe this might have actually gone out a little bit further. Well, how can we define these pixels? Well, the definition we're going to say is that this is a boundary pixel that only has one neighbor. So here's a pixel and here is its one neighbor in this little sort of 3x3 neighborhood that we've got here. And once we see a little pattern like that, we can say, well, actually we don't really need this pixel because the boundary kind of comes in here and then it goes out there, so we don't need to have that little extra bit. So we want to remove those kinds of pixels. We want to remove other pixels as well too. But first we'll start with that. Well, here's a little bit of MATLAB, and we're not going to have too much actual computer code here, but this is useful for giving you some idea of how you can do a little bit of image processing in more detail. Another thing that we're going to be interested in is that sometimes these pixels dangle out here and we want to get rid of all of them. Okay, so that's what this little code is going to do as well too. So we've got a while loop here, okay, and this says effectively while the image has been changed, we're going to redo all of this processing several times until we get rid of all of these dangling pixels. And we're going to want to do this all across the image, and we don't want to have to scan the whole image or whatever, so we're going to want to find just the pixels that lie on the boundary. Okay, so we're going to find the pixels that lie on the boundary right here. That's our list of pixels right here. We've got the length operator, which tells us how many pixels we've got on the boundary. And then we're going to look at a little 3x3 neighborhood. And so this is a little MATLAB kind of convention where you can pick out of your working array. This is our, sort of if I go back, this is the array right here. This is our working array. And we're going to pick out for at the current position in that image. We're going to, so here's the row coordinates, that's the SR, and the column coordinates. We're going to go back one column and ahead one column, and we're going to pick out a little chunk right here. Similarly with the columns, oh sorry, that's with the rows, and similarly with the columns, we're going to go back one column and ahead one column. So that gives us a little couple of columns, 3 columns wide and 3 rows wide, that's wrapped around the current position SR. And that gives us our little 3x3 neighborhood. Once we've got our neighborhood sort of isolated for this particular boundary pixel, we can count the number of boundary pixels that are in that neighborhood. And so that's why we use the sum command. Sum normally works on a one-dimensional array, so we start with a two-dimensional array, we do sum once, that gets us down to one-dimensional array, we do sum again, that gets us down to just a count we've got. If our count is less than 3, that's 0, 1, or 2. Well, it wouldn't be 0 because we're already looking at pixels that are on the boundary. It could be 1. That would be an isolated pixel that's just in the middle of nowhere. Or it could be 2, which is the case that we're interested in here, where we've just got 2 pixels inside that area. In any of those 3 cases, 0, 1, or 2, we don't need that pixel, and so we set it to 0. And we make note that we've actually changed something in the image. And then we kind of carry on. So we process all the way through the image and we've changed something. So once we've done that, then it goes back and says, oh, I should do it again the next time. Anyway, so once we've finished all of that, that's going to remove all of those dangling pixels. Well, that's not the only kind of pixel that we've got to remove. And here's another kind of example. So here is our boundary coming up through here. It's definitely gone through the starred pixel. It also goes through this pixel C. And we're not quite sure exactly, for the sake of the argument right here, which of these pixels it's gone through the question marks. But we do know it sort of started here, it went through there, and it went out this way in some sort of direction. Well, what we can say here is this C pixel is again surplus to requirements. We can go directly from this pixel here by our diagonal connection to this pixel right here, and we didn't really need the fact that this was a marked boundary pixel. We can get rid of that. So this is an example of kind of image morphology. Here we're going to work on a pattern of a little 4x4 neighborhood, and whenever we see a little pattern like this, we can say, well, if I got a C pixel right here and I see this sort of pattern, I can get rid of it. Okay, well, this pattern could have come in different flavors, so here's the C right up here, still going through here. Alternatively, it could have gone this way and got it right there and go right there. So we need 4 different patterns. But once we've applied all 4 of those patterns, we can clean up the image data by getting rid of all of these pixels. So here's just the annotation. So these are the boundary points that we're going to keep. Those are the stars. This is the one we're going to remove, and these are the ones that we don't really know exactly which one. We can allow different things right here. Okay, so this is a kind of example of image morphology. We're not interested in the values of the image. We're interested in the patterns that the image takes between the 0 patterns and the 1 patterns. And there's lots of different examples of that, and we'll be looking at a couple more of those throughout the course of lectures here. So once we've done all of that, here was our original image, and if we go back to look at the zoomed in version, we can see that there's some of these extra pixels right here. So these are some of the pixels that we were talking about, either the dangling pixels or the little surplus pixels that we've got right here that we don't really need. And after we apply those algorithms that we've just looked at, we can see that it's been cleaned up. Here's our circles again, and you can see those pixels that I had circled before, they're now missing. Our algorithm has worked fine and cleaned it up right there. So that's given our boundary a little bit of a cleaning, and it's going to make our other algorithms a little bit easier to work with. Well, we've cleaned up our boundary. Now we've got the problem that all of our pixels are in some sort of an order, and we want to be able to find a boundary that goes all the way around the object in a particular order. This is going to be a little bit more complicated. The key to it is to look at a set of pixels, and we're going to say here, we're currently at this particular place, and we want to go to the next pixel. So the pixel on the boundary is the x, and the other x is the next pixel that we're going to go to. And what we're going to look at is we're going to notice all of these different directions around here. So we're going to number the directions in this particular kind of clockwise sort of order, sort of 1, 2, 3, 4, 5, 6, 7, 8. And what we want to do is we want to walk around the boundary. We're going to walk around in a clockwise order, and we're effectively going to keep our right hand on that boundary, and we're going to walking around. This is an algorithm that allows us to do that. So if we have our boundary at a current position, we can look at where the pixel last came from. What direction did it last come from? So that's our last direction right here. And now we're going to say, well, okay, if I came from this direction, what order should I check the pixels going around the current pixel to see where I should go to next? Okay, so here's our current pixel. We've come from the last, and here's the different directions. And what we want to do is we want to say this is the next direction that we want to do. So in the case of this one right here, as if we came from here and we want to go there, that's in this direction. That's in the 3 direction. So we want to be able to say, okay, the last move was 3. Where should I start in order to look around the boundary to find it? And this is, since we're going to go around in a clockwise order, we're sort of looking, well, if I come this way, the first pixel I want to check is this one, and then this one, this one. So I want to check the pixels to see if that's where the next boundary pixel is going to be. So I start with 8 right here, and then 1, 2, and 3. So that's the order that I want to generate. And it turns out this little expression right here is the expression which will generate that order. If I step from 1 to 7 as I go around for the 7 possible directions, that will take the last move 3, and for stepping through 7 will generate these 7 directions as the directions to try as we walk around the object. If there's no pixel right there, we go on to the next one. If there is a pixel there that we've already cleaned up, that's the one that we want to go to. So we get stuck right there, and that gives us the direction that we've wanted as we walk around the boundary. So if we apply this slightly convoluted boundary tracking algorithm to our data, we get something like this. Originally, we've taken our d-spurred boundary with all our morphology, and we've got our cleaned up sort of boundary right here, but it's unorganized. And we put it in the image, and when we use that boundary tracking algorithm, we get out our point set. And just to show that it worked okay, here you can't see that they're in any particular order, but I've taken the tracked pixels and I've drawn them here on another image, and you can see we've got all the pixels right here as they should be. Well, these tracked pixels are what we're going to be needing for our next process, which is the breaking up of this boundary into the straight line segments. And in order to do that, we needed to have all the pixels in order. Right, so what have we done right here? We've looked at really pretty much pre-processing type operations, but they're the first parts of actually recognizing the objects. We've got a way of finding a boundary from our binary images using this bw_parem command. We've got a way of taking that boundary and cleaning it up using some image morphology type operations. And now we've taken all of those boundary pixels and turned them into a list of consecutive points. And what we're going to do next is try to find the straight line segments that describe that shape in the image. Thank you.